Hello everyone, welcome to my YouTube channel. So in this video we're going to look at the Lobitals Rule, which is an approach of evaluating limits of functions that satisfy a particular condition. Okay, so you recall I said that there are some limits that we will have to evaluate by certain approach. For instance, I said if you are given something like the limit of, let's say, and so if you do a direct substitution here, of course you're going to get in the numerator you will get 0, and in the denominator you will also get 0. Okay, so and you will see that this is going to lead you to a situation we call indeterminate. How do you evaluate such limits? So in this case, it is possible to cancel out common factors in the numerator and denominator and then do your direct substitution and still get your answer. However, there are some functions that you can do this kind of cancellation from the denominator and the numerator of your fraction. Okay, so how do you establish such limits? All right, so and then we said that you can use the approach we call the Lobitals Rule. So we say if you have two functions that are differentiable, that means you can differentiate them where the denominator is not 0. That's your g cannot be 0. And so we said if you do a direct substitution of x going to a, that means x equal to a, into the two functions, and you're getting either 0 over 0 or infinity over infinity. This infinity over infinity here represents both positive and negative infinity. Then this method says that you should just take the derivative of the numerator, take the derivative of the denominator. That's why we have f prime here all over g prime, and then do that substitution. Whatever you get is the value of that limit. And then we're also saying that assuming you do the first differentiation and by direct substitution, you're still getting 0 over 0 or infinity over infinity, then you should also differentiate again. All right, so here we have examples. The first example is here. You can see, of course, if you do a direct substitution here, ln of 1, logarithm of 1 is 0. And if you substitute here, 1 minus 1 is also what? 0. So you have 0 over 0. It satisfies the Lobitals rule. Okay, so that means we need to differentiate. And so if we differentiate ln x here, we are going to get 1 all over x, and then over, if you differentiate this, you will get 1 as x goes to 1. So at this point, we can do a direct substitution, and if you do that, we are going to have, this will be 1 all over 1, and then everything is over 1, and this is going to give you 1 as your solution. All right, the example 2. If we substitute x as pi, you're going to get the sine of 2 pi, and you know sine of 2 pi is actually equal to 0. And then if you substitute here, you will have pi minus pi, which is also 0. So it satisfies the condition. And so at this point, we can take the derivative. If we differentiate, remember to write your ln. If you differentiate sine 2x, you are going to get 2 cos 2x. And that is all over. If you differentiate this, you're going to get 1, because this will give you 1, and pi is a constant, so you will get 0 there. And so that is to say that our derivative is, our limit. Remember, this limit here is going to pi. So if we substitute here now, we're going to have the 2 cos 2 pi all over 1. And that is going to give us 2 cos 2 pi. So we can actually write it as 2 cos 2 pi, or we can evaluate cos 2 pi to get the value of it and then multiply by 2. Right, so we go over here. The next example here says solution, that we should also evaluate this other limit. First of all, remember the first thing to always do is to check that it satisfies the condition. So if we put x as 0 here, exponent of 0 is 1, and if you put 0 here, you have 0. So 1 minus 1 is 0. That's ordinarily all over 0 squared is 0. So it satisfies it. So we'll try to now use the method that's the Lobitals rule. So if we have, then we'll have to differentiate the numerator. If we differentiate exponential x, we'll get ex. If we differentiate x, we'll get 1. If you differentiate minus 1, that's 0. All over, you differentiate x squared, you are going to have 2x as x goes to what? 0. And then if we do a direct substitution here, you would see that we will still get 0 over 0, because e raised to power 0 is 1, minus 1 is 0, and then 2 times 0 is still 0. So that is to say, you have to differentiate again. So if we differentiate again now, exponential x or ex will still give you ex, then differentiate 1, you will have 0. All over, differentiate this, you will have 2. So if we now direct substitute here now, we'll have e raised to power 0 all over 2, and that's going to give you 1 over 2 as the solution. Okay, so for example 4 now, we have solution here. Okay, so you can see that if you do a direct substitution here, sine of 0 is 0, and if you divide by 0, so you have 0 over 0. Okay, so at this point we can take the differentiation of the numerator and denominator, and that's going to give us cos x all over the derivative of this is 1 as s goes to 0. And if you direct substitute here, you are going to have cos of 0, which is equal to 1. And then here we have this other one. So you can see at this point, we can actually factorize this denominator. And so that approach can work here. So if you factorize this denominator, you're supposed to get something like x. Okay, so this is what you're going to have. All right, now, but at this point, we want to check if L'Hopital's rule can also work here. If you put your x as minus 2 here, you will get 0. And then all over, if you put your x as minus 2 here, that's 4. Then this will give you minus 6. 4 minus 6 is minus 2 plus 2 is also 0. Okay, so if we differentiate now, we are going to have the limit of, differentiate this, you will get 1 all over, differentiate the denominator, that's going to give you 2x plus 3 as x goes to negative 2. And so at this point, we can actually substitute. And if we do that, we are going to have, this is going to be 1 all over. If you put x as minus 2 here, you have minus 4 plus 3. And that is 1 over minus 1, which is actually equal to negative 1. All right, so, and that's all we have. But in case you want the one that will give infinity, let's say example 6, we can actually use this also. Okay, so at this point, if we do a direct substitution here, infinity plus 2 is infinity, and if you put anything here, you will still get infinity. So what do? Differentiate. And if we differentiate here, we are going to have what we got here, and as s goes to infinity. So at this point here, what do? If you substitute here, you are still going to get infinity in the denominator. So you can actually use the approach that we thought for limits going to infinity. So what do? Divide everything you have by x. If we divide this by x, we'll have 1 all over x, and then this is over, this is going to give us 2 here. If we divide 2x by x, and then you divide 3 by x, you get 3 over x. Okay, so at this point, if we substitute now as our s goes to infinity, we're going to have 1 all over infinity over 2 plus 3 over infinity. And so this is equal to 0 all over 2 plus 0. So 0 all over 2 is actually equal to 0. So okay, so that's about L'Hopital's rule for evaluating limits. Please kindly subscribe to our YouTube channel, and like, comment, share our YouTube videos. We'll see you in our next video. Bye.